Alright, so the goal here is that you want to understand more about uh, what vtables are and um, how they are uh, useful in allowing the compiler to uh, implement runtime polymorphism. So to get started, I will first create a simple example which shows uh, what is runtime polymorphism. So suppose we have a class called base and this has a function called virtual void uh, print me and that will say basically uh, base. So this is our base card. Then say we have a derived class public base and this will also have a virtual print me and then this will print derived. Now suppose that we also have a function called print class and that takes a reference of base and will come to uh, why we need base, but ultimately what we want to do is that I will simply say base print me. Okay, we need to have these public, both of these are public. Okay, so then we can say int main and then yeah, we can say base. We created a base object, we created a derived object, we created a, then we are asking it to print base and we are casting it to print class. Now notice that the print class is taking uh, the object of type base and then print class is also able to take the class derived. So the reason is that because derived is a derived is deriving from base, so all the methods that are available on base will be by default available on derived. So it's okay to typecast derived into base. Uh, so let's run that. Let's say clang plus main.cp. It's not saved right now. So not saved main.cp main and then we can say okay, so this prints base and this prints derived. Uh, what has happened here is that uh, we have basically passed different super classes of base and the correct function was called. Now we understand that derived was the type of derived was casted to base and that happened automatically. Now what we can do is that instead of doing it automatically, let's say base we say derived and base and then we cast derived to it. So notice that we have basically casted the derived pointer usage of type derived to the pointer of type base. Now we can pass derived base here. Now what we would expect, so previously in the example we were passing the whole object and internally what was happening that this derived type was getting typecasted to base, and still it was able to print the correct function. On the first look, one can guess that since the pointer is of type base, all it should know is that uh, this is the function that I need to call. But with some mechanism, even with the base pointer, it is calling the right function. So let's try out this again. In this case, we are explicitly typecasting it to base. Let me compile it and then run again. So it's still printing base derived. So what we want to do is we want to understand the mechanism of uh, why this is happening. So the the way this works is that when we are uh, typecasting the base, typecasting the derived type to base type, we are getting uh, a pointer to base object that is inside the derived base. So uh, we'll go into detail like by showing what exactly is happening. But for now, I want to show you something where we are going to show you the difference between uh, the derived base and the actual pointer. So derived base, and we can say this is pointer type. So maybe size t or maybe ptr type. Is there a ptrt? Not really. So let's assume it's long. Okay, and we want to. Okay, we don't actually need to typecast it first. What we can do is we can do derived base and uh, subtract it with derived. Okay, sorry, derived. Derived. Okay, okay, what is the problem? Derived and what is wrong with this? So we have derived type. Okay, let's use pointers. Okay, okay. Now we want to static cast a star, and then we want to pass the pointer of derived. Okay, we want to have derived star derived equal to new derived. Okay, then we can just say this. Now print class is going to take base. There is no base needed now. Okay, okay, it can actually. Okay, So we can quickly compile this, and so we can see the same thing again. So this is the derived pointer, and after casting it is still able to print the thing. Okay, now let's see what is the difference between the derived pointer and the base pointer. So for that we have auto diff equal to derived minus derived base, but that obviously won't work. So what we can do is there a PTR type? No. What can we do? We need to pass it the same type of parameter. So let's see. Oh, we can typecast to white star derived base minus. Okay, okay, it's time for asking chat GPT. We want to find out the difference between the pointers. So here we go. So what I want to show is that this derived base is inside the derived object. Okay, so white star, okay, ptr diff. Okay, so the thing is that we want to interpret this as car star, car star, and then we want to print the diff. Okay, so it says that the difference between the two is 0. That is interesting. Okay, we'll come to that again. So this says that the difference is 0. The difference is 0. Okay, now let's see what about uh, creating a second class called base2, and this will again have a virtual void print my id. Okay, and then derived is going to uh, derive from both public base and base2. Okay, now we are going to do the same thing for print class id, and this time we are going to take base2 as input, and then we are going to say print my id. Let's see what happens now. Again we have derived and we have base star. Similarly we can say that we can do base star derived base 2, that will be static cast base 2 star. Okay, and then we can say print class id derived base 2. Print class id. Let's see. So what we expect uh, is auto base 2 equal to no base. We expect that uh, similar thing what was happening before. So derive base, is it overriding? Not still, we should print it. Okay, print my ID says derived ID. This is base type ID. Okay, and compile again, run. Okay, we can see the base 2 ID, derived 2 ID, same thing. Now let's see the difference between the derived base 2 and derived. Let's see what is the difference. Okay, let's see. Oh, the difference is 8 now. It says the difference is 8. So it says that the difference is 8. Interesting. So we have a clear picture in our mind. So here is how derived. So if I create a object and let me switch quickly to Salitra. Let's create, go to a different place. Okay, let's see. So what we are seeing here is that, so let's say this is the derived object. This is the derived object, and because this is the derived object, the derived pointer points to this place. This is the beginning. Okay. This is where derived is, and as we have seen, when you typecast it to base here, when you typecast it to base, you get a base star pointer, and that is also at the same location. So we are seeing that derived base is also at the same location. It is also pointing the same thing. Interesting. It is also pointing to the top of the derived object. But when you are typecasting it to base 2 star here, we are seeing that the difference between two is 8. And what remember that every pointer is addressing a single byte. So what this is saying is that we have derived base pointing to here, and this is 8 bytes. This is 8 bytes. Interesting. Okay, so that this is one uh, one interesting thing that we understand. Okay, let's see what is the size of derived object. So if I say size of derived, the size of derived object is 16. Interesting. So what we are saying is that there are 8 bytes here and 8 bytes here. And remember that derived is inheriting from base and base 2. Okay, so this all we can see. Now what that is suggesting, that when you derive a class from two classes, they go in a certain order, and when you typecast a derived class to its base classes, you don't just get the initial pointer. What you get is the pointer of the sub object inside it. So when you typecasted to base star, you got the beginning of the uh, derived object. That is because these 8 bytes are corresponding to base object, and when you typecast it to base 2 object, you got something that is 8 bytes ahead of uh, the derived pointer, because that is where the derived base 2 lies. So that is all interesting. Now, what is contained in these 8 bytes? That is what we want to understand, and that will help us understand how this polymorphic actions happens. So polymorphism is a fancy name, but what is happening that when you called, first you took a derived pointer and then you casted it to a derived base pointer. Now this base object, remember that if you simply copied the whole object like this, then ideally this base, the function address that you have here, it should point to this function. It should print base. But in reality, when you typecasted it to base, it was still pointing to the correct override. Was still pointing to the correct override. So somehow uh, this object here, this object here has something, some kind of uh, address that is present here. So let's see what that is. So I'm going to move these a little here. Yeah, that is good. Okay. So obviously we know that uh, when you write that go to base and then go to print me, there must be a address stored here somewhere. There must be some mechanism which tells us uh, where to find the print me. Print me. Okay. And similarly for base 2, we know that there must be some place where they have some mechanism on how we uh, how we know what is the correct print my id to be called, and if there is a override, then we want this to contain basically uh, the overridden function address and not from the base object. Okay, so the the thing that we can do, we can ask ChatGPT that I want to understand the object layout, uh, layout and vtable layout of the classes in main.cpp. What are the clang plus plus flags I should use? So it's thinking the way it happens is that we have something called a vtable. So every class will have a vtable. Every sub-object will have a vtable, and that vtable has entries on which functions should be where. So the vtable will have an entry corresponding to print me. It will have an entry corresponding to print me some address. Okay, and there will be another vtable uh, which will have address for print my id. So we'll come to that. It's better to print things end to end. So let's see. Says main.cpp. So we are using xclang fdump record layout. Okay. And let's save it to something like vtables record layout.txt. Okay, let's see what is in record layout.txt. So there is a lot of information here, and that is because we included the include header basically, and yeah, it's not readable right now. So instead what we are going to do is that we will have to, is there a way to filter by, yeah, so we can filter by derived. Okay, okay, so it's much better if we simply say that instead of print me and this, we can say return 1, can say return 2, okay, and then this can be also return 3, and this can be return 4. So I want to avoid basically printing things at all. Cool. So now we can remove these for now, and we can remove this. Okay, this will make sure that we don't have much uh, a lot of info. Yeah, actually we can print it here as well, since now it's testing. So let's look at what is happening. Okay, so going back to our figure. So it says that base, the type of base is just a pointer, and the non-virtual base relevant type is also just the pointer. You can ignore this. Here is the interesting part. So first is base, and let's look at what base is saying. It's saying that base, the class base 0, it's starting from 0, and the the value here is base vtable pointer. So obviously it's just saying that there is a vtable pointer, and the size is 8, d size is 8. So this is basically saying that the the pointer is of 8 bytes, so 64 bits. That makes sense. It's a pointer. Okay, so the base class type just has a size of 8, data size is 8, aligned to 8. We can ignore this one. It's probably related to non-virtual size, not align. Here we can see uh, uh, what all is actually uh, present in the. So when you write a simple function like this, what all actually gets automatically inserted by the compiler. So it's the base definition. There are definition data, and automatically we have few things, and we can write it out here. And these are the automatically generated things. First is the default constructor, second is copy constructor, third is move constructor, fourth is copy assignment operator, so that you can say a equal to b, and then fifth is again move assignment operator, so you can move the ownership, finally the destructor. Okay, so these are the things that are automatically generated, and you can see it here. Okay, then comes so sorry, this will be a little above. And then comes the access declare a token. It's called a public, and then you have the actual function. So uh, uh, saying that it is a virtual method, virtual implicit inline, and the type is int and taking no parameters. So it's returning int, taking no parameters. And then inside saying it's just a return statement. That's fine. Then we are not seeing it here, but internally they will uh, declare uh, the different methods like the uh, basically assignment operator. Okay, and then the second thing is uh, move operator, and finally, so you can see this is the call to operator, and then this is the convert taking R value and giving us the L value. This is taking const parameter and returning the normal parameter, and then finally it's uh, declaring a destructor. So you can say there are at least 2-3 methods here. 2-3 methods declared. Okay. So finally the layout. Look at this. This was all for base type. So yeah. Now let's move to base 2 type. So this all was for base. Similarly, here will be 2-3 methods as well. So we can just copy that. Again, there will be few functions, default functions. Don't to worry about that. Again, you can see that the type is just a pointer, and here it says that it also has a v type pointer. So now finally moving to the uh, our derived class. So let's see what is in the derived class. So it says that class derived, and you can see that this is same for the base 2. Base 2. Yeah. And let's see. Now the final thing is for derived. And let's see what is in derived. So it says that class derived has 0 offset, it has class base, which is the primary base. That's interesting. There is something called primary base. Uh, so we have at the 0 offset we have the primary base, and that primary base in this case just base. So base has primary base, and it has the base vtable pointer. So as we know that the base is just a size of base is simply 8 bytes because it contains a single vtable pointer, and then comes the base 2, and it will be at offset of 8. As we remember, if I go back to here, we concluded that the offset, the difference between derived base or derived and derived base 2 is 8 bytes. That the reason is that uh, 8 is the size of the pointer to the vtable, and then the total size is 16 because you have a pointer here and you have a pointer here. So these are the two pointers that I stored in derived. Now let's see what happens uh, when you when you call a function on derived. How does it figure out what is the right function address? How does it calculate the right function address? Oh, it's 16 bytes or 2 pointers. Okay. For that, we need to go a little below and see what is the vtable layout. So see, let's see what is inside the vtable. Let's see what is the vtable. Interesting. So here we go. Okay. So this vtable was pointing to the actual vtable, and this vtable has few things. We are going to see what is the vtable. First thing it has is offset to top. Okay, so that is the first entry, and then the second entry is something called base RTTI. Okay, let's see what that is. It says that the base RTTI is for runtime type information. The base RTTI has only one value, and that value is base 0 and then vtable address. Okay, so this is first, this is second, and finally the last entry is int base print me. This is interesting. So in the vtable we have stored base print me. Okay, so this is the table, and then we have a vtable indices. So this is the vtable pointer, and then we have the vtable indices. This will tell the this will basically have the mm, mapping from index. So this is the index, and the uh, where is the function? So what it is saying is that ignoring the first two things, the index of base print me is 0, and that is stored here. Base 2 is similar, so I'm not going to repeat that. Let's look at the vtable for derived. So remember that uh, there were two vtable pointers for inside the derived. One is for the base and another is for the base 2. So it says that the original so first we have to answer the question, where is the vtable for derived? So you can see that the sub objects, the object that derives from base and base 2, they have both their vtable pointer, but where is the where is the uh, vtable pointer for derived? And the question is that the vtable for derived is the first one, so it stores the vtable, its information in the primary base itself. And let's see what all it has. So again, it's going to have offset to the top, interesting, offset to the top 0, and then it has the derived RTI, derived RTI, and inside the derived RTI we have a few things, so let's look into them. It says that both base and derived are at offset 0. Interesting. So it says both are at 0, and then it has the base print me, and then it has the base, it has the, sorry, instead of base print me, it has the derived print. Similarly, it has the derived print my ID. Then comes the interesting part. So this was 2, this was 3, no, but this is 0, this is 1. Then it says that the offset to top is -8. Okay, it says that offset to top now is -8. Okay, and then it again has the derived RTTI, and this time it has the value base to 8 and then vtable address. You'll understand what exactly is happening here. But the interesting thing is that if somebody comes here, imagine you have typecasted to 8, and then you want to find out what is the actual pointer, you know that from here and here. So that's why it's called runtime type information. So the runtime will know that although this is typecasted as base 2 star, base 2 star, the real object that this is part of is derived and sits -8 above, 8 above. So that is useful, as we will see. Then it has, again interestingly, it again has a int derived print my ID, but this time there is a comment saying there is a this adjustment of -8, and that is applicable when you are calling base2 print my id. What is happening here is that let's say you called base, you have typecasted from derived to base2, and then you called base2 and then print my id, and print my id is using uh, this pointer. Now what this is saying is that by default this is this equals the uh, pointer of object, but here it's saying that in this case this is going to be base 2 minus 8, that is derived star, which makes sense because uh, this this function is being called from uh, derived, not from base 2, right? So if, this this pointer needs to be adjusted. Okay, so then there are something called thunks. So as you can imagine, thunks is basically before you call this base to print my id, you have to basically run this thunk, and that thunk will adjust this by subtracting it to -8. It's for print my id, and the vtable indices are for simply 0 and 1. So what all happens here? What all happens here? So when you do base and base 2 and then you cast to base star, what is happening? So in this case, when you are casting a derived to base star, is going to first check uh, derived.tti, and that will tell that if you want to uh, cast me to base, what information you should keep in mind. So the information you should keep in mind is that base pointer is at 0 as well as the derived pointer. So what that means is derived base, in this case derived base is simply derived plus 0. There is nothing to add. But in case of derived base 2, the derived, if you go to here, when you typecast it to base 2 star, the information says that RTI says that base 2 is at 8. What that means is that you have to remember that derived base 2 is derived plus 8, and when you want to go back to derived for this, you have to remember that derived base 2 minus 8. Okay, and then what happens when you actually call the function? When you actually call it here, print me will, because it's a virtual, it will first check the vtable index. Okay, and there are two indices here, 0 and 1, and they correspond to this 0 and 1. What that means is, in this case, because we have overridden both print p and print id, we are using the functions from derived. Imagine that there is something called virtual int return 3. Then will since we have not overridden anything here, we'll see the function name here. So see, so when we are calling base to hello world, we will actually use the vtable for uh, vtable for print. And interestingly, there is no index generated here for hello world because it was not used. So we are going to use it now. Interesting. So you can see that there is an entry here, and if we go into the base 2, we have the entries for things here. Okay, now we can ask what is the sequence of steps that happen at runtime when we call derived base 2 and hello world, and here are the vtable indices. So our understanding is that when you typecast it to base 2, we knew that what our vtable is, so we'll know what the function location for hello world is. But before calling hello world, okay, we don't really need to do this adjustment this time because base 2 hello world is defined inside base 2 itself. It's interesting that we are doing the adjustment for print my id, but we are not doing it for the hello world. So when we call derived base hello world to Okay, so this points to from your vtable dump we can infer multiple inheritance with base at offset 0 and base 2 at offset 8. It's fine. Base 2 was started d plus 8, that's fine. Okay, each each polymorphic base object has its own v pointer. So there are at least two v pointers stored inside a derived objects. That makes sense. So there is, it's interesting, says client won't devirtualize. So it's something to understand that there is something called devirtualization. So we'll probably try that out. Devirtualization. So we when we casted it to base 2 star, it did this pointer equal to d plus 8, and then it loaded the v pointer from the base 2 subs object. Then we create, then we know the signature. Okay, so it knows the signature, and then we found out what is the slot for hello world, and then we got the function, and finally we passed the this pointer. Remember, this is not adjusted, so we are directly calling the function. So we are loading, we are doing one pointer load for vtable, then we are loading from vtable because you want to know the function address, and then finally we are calling the function. So the steady type is base 2 star, so the call uses the v pointer located at the start of the base 2 subobject instead of the derived. Now derived has a secondary table for base 2 at offset 8. So when we, so this was the uh, derived v0 table address. Now this is the derived uh, this is the second derived base table address. So after the RTTI, this starts the vtable address. So inside this pointer points to basically this here. Yeah, and this will point to this, or not really. So we can point to this, and this will point to this. So the two cave tables are contained in one. First two things are only offset to top and derived IOTI, and then we have the actual vtable entries. In this case we will have the hello world as well. And for derived, there will be only two indices that are overridden by uh, derived. So what extra we can do is we can actually override the, okay, we don't need to do that. We can go back to our understanding here. Point to the vtable whose relevant trace based to hello world. So why there is no thunk for hello world? The thing is that derived print my id appears in the page 2 vtable region with a this print thunk, It's a plain function pointer, no thunk. The reason is that print my ID is an override, or at least resolves to derived implementation. Its implementation likely expects this to be a derived pointer. So what this is basically saying that because we are going to call this in reality, then if somebody has written the code to use this, expects that this is derived object. However, if somebody has written this using this here, then they have assumed that this points to the base2 object. So if you are not overriding hello world, then there is no need to do this adjustment. So this is what is happening. We do uh, this setup. So in the starting, it's this setup. We set derived base, and then we load the view pointer, and then we load the actual function definition, and then finally uh, we select we call the function, and then we don't need to do any setup for hello world. So offset to top and TTI, what are their uses? So they're not used for plain virtual dispatch, but they matter for things like dynamic cast. When you're casting from the base pointer to the derived pointer, it needs to know what is the uh, what is the offset that it should adjust. So it has to know that if let's say you want to let's say you have a derived base 2, and you you want to you have derived base 2 derived base 2 that you have typecasted, and then you want to go from derived base 2 to derived object again. Want to go from to derived star object again, that is the original object address. So in this case, what we need to understand is that derived base is basically need to subtract 8, and that is because that is the offset from that. So this is where the base sub object is, and when you are typecasting using dynamic cast, it will use this uh, RTTI that is present here to do this. So the RTTI will help you tell that, look, the address that you have right now is at offset 8 from the base pointer. So you can subtract 8, and then you will get the you will get to the actual derived object. So similarly for type ID base 2 PTR, if you have already typecasted to base 2, like we have done here, like we have done here, and then we want to know what is the if type ID of derived base. Okay, I to not will need to include type info. Okay, equal type ID of base, then derived is a base. So note that in this case, both derived base and derived derived base is pointing to derived base is pointing to both base subobject as well as derived object. So both are true. Now same thing will not be true for derived base 2 is not equal to type ID derived. Is not pointing to derived object. Derived object base 2 is pointing to a derived object. So let's see. Testing. Okay, so says that derived base 2 is not pointing to a derived object, which makes sense because we know that derived base 2 points to a base 2 star object. Now derived base, okay, it's pointing to base as well as pointing to the, so both this should have been correct. So let's ask. Okay, says that type ID gives the static type of expression unless expression is a GL value, an L value, X value of a polymorphic type. A pointer is not a polymorphic object, so type ID derived base is the type info for base star, not base and not derived. And it does not look at the vtable. So you are comparing base star with the type of base. Also, there is the second logical impossibility. Single type can't be both base and exactly derived at the same time. Okay, interesting. What we mean is that dynamic type of the pointed to object. To ask the RTTI vtable what is the dynamic type of the object behind this pointer, you must apply type ID to the object, that is star pointer. So what you're asking is that type ID derived base dot name, then even though the pointer type is base star, you will know that the type ID will tell you that although even though I'm pointing to a base star, my actual type is a derived type. Okay, and similarly again, even though I have a pointer of type derived base 2, that is a pointer of type base 2 star, I will still know that the type is derived uh, by looking at the uh, looking at the RTTI information. So what happens at the runtime when you say type ID derived base? Given base is a polymorphic, derived base is a GL value of polymorphic type. So type ID does take the address of the object, so it points to t plus 0. Load the vptr from the object's word. Okay, from the vtable header finds the RTTI pointer you dump, shows it as base RTTI derived.jci. So okay, return the std type info object reference. No, is both base and derived. RTTI identifies the most derived dynamic type. So it always tell you that it's derived. Similarly, rows loads the base to side vptr. Again finds the RTTI, still derived RTTI, and then returns the same object. So if you look at the RTTI here, still the derived RTTI is to vptr, then finds RTTI, it has the same dynamic type. Goes from here to base 28 vtable address. RTTI is still derived RTTI. So the RTTI is always derived RTTI, and the vtable addresses start from here. Similarly, alright, so this gives a nice overall image of what is happening. You actually uh, call a virtual function basically. So the base table and these are here. The base table RTTI address is here. This is where it starts. Okay. So yeah. So this is the internal mechanism by which at runtime we are able to figure out first what is the true type, and second what is the right function to call. Uh, uh, what is the right function to call with the correct this adjustment. So that's it.